In this video, I'm going to explain you about what is a subspace of a vector space. Okay, so we have this definition. So this is the definition of a subspace. So let V be a vector space over F. A non-empty subset W of V is called a subspace of V if W is itself a vector space over F under the operation in V restricted to W. Okay, so the meaning says here is that first of all we have we have V. Okay, we have V is a vector space over F. Okay, V is already a vector space over F, and there we have taken a W to be non-empty set. Okay, W is not empty, W is a non-empty set, and W is a subset of V. Okay, W is a subset of V. Then okay, W is a subset of V. Then this W, okay, then W is called a subspace of V if W is a vector space. W should be a vector space if W is a vector space over F under the operation of V. Means it is forming under the same operation as V. Okay, so V should be first of all, V should be a vector space, W should be non-empty, and W should be a subset of V. Then this W is called a subspace of V only if, okay, only if this W is forming a vector space itself under the same operation of V. So that is about the subspace. So we have this theorem now. We'll try to prove this theorem. So let V be a vector space over F. Okay, I'm taking a vector space over F, a non-empty subset W of V. We are taking W to be a non-empty, and it is a subset of V. Then this W is called a subspace of V if and only if for all xy belongs to W. You take all the xy belongs to W and alpha belongs to beta. Then first condition is that x minus y will belongs to W, and point number 2 is alpha into y belongs to W. So let us prove this theorem. So first of all, let us assume that W is a subspace of V over F. Okay, so suppose W is a subspace of V over F by the definition. Now see, W is a subspace, then W is a vector space. Okay, W is a subspace of V means W is a vector space over the field F under the same operation of V. So if W is a vector space, first of all, W should be an abelian group under addition. Okay, so since W is an abelian group, we have to show that W is an abelian group. Okay, so since W is an abelian group, W is a subset of V. V is also abelian, so W should be a subgroup of V under addition. Okay, so since W is a subspace of V, W should be a subgroup of V under addition. Okay, it is a subgroup of V under addition. So we know how to prove a subgroup. So how we prove? So let us revise about the subgroup. So how to prove a subgroup? Suppose H is a, we want to prove H is a, first of all, H should be a subset of G. Then H is a subgroup. It's a subgroup of G. We are talking under addition. Okay, under addition, if X minus Y belongs to H. Okay, if X minus Y belongs to H. So if we can show X minus Y belongs to H, then H will be a subgroup of G. Okay, so here, since they have given you W is a subspace of V, W should be a subgroup of V under addition. Okay, so I take two elements from W. Since W is a subgroup of V, okay, since W is a subgroup of V, X minus Y should belongs to W because it is a subgroup under addition. Okay, so that why X minus Y will belongs to W. So this condition shows that condition 1 is true. Okay, condition 1 it holds. Now we want to prove for the second condition. Already we have what? We have that W is a subspace of V. So since W is a subspace of V, it should be a vector space over the same field. It is a vector space over the field F under the same operation of V. Okay. So since W is a vector space, it is closed under the scalar multiplication. So by the definition, W is closed under the scalar multiplication. So I take one element from W. Okay. Then I take an element from the field. Since W is closed under the scalar operation, alpha into Y will also be in W. Okay, since W is closed under the scalar multiplication, so that why alpha into Y also will belong to W. So this shows that condition 2 is also true. Okay, this shows that condition 2 is also true. Now we'll assume that condition 1 and 2 is true. Then we try to prove that W is a subspace of V over F. To prove a subspace, first of all, let us prove that W is a vector space over the field F. Okay, so by condition 1, okay, by condition 1, see if we look the condition 1, from here we have what? I'm taking XY. Here you can see that I took XY from W, and then X minus Y should be in W. Okay, so from this condition, we can say that W is a subgroup of V. Okay, under addition. So W is a subgroup of V under addition. Okay, so we have that W is a subgroup of V under addition. Now V is abelian group. Okay, so every subgroup of an abelian group is always abelian. Okay, since V is an abelian group under addition, okay, it is an abelian group under addition. So we know every subgroup of an abelian group is abelian. So that's why W plus is an abelian group. Okay, so we'll get here W plus is an abelian group under the same operation, addition. Now we'll try to prove the fourth condition of the vector space. Okay, we are trying to prove the fourth condition of the vector space here. Okay, so the first I'm taking alpha beta belongs to the field, and I take two vectors from W. Then the first point was alpha x plus y. Okay, so this is equal to alpha x plus alpha y. This belongs to W. Why it belongs? By condition 2, this quantity, okay, by condition 2, if we say this condition number 1 is what? Alpha x plus y. So I got here this in scalar multiplication, we get alpha x plus alpha y. I have to show that this is in W, but this quantity is in W, we know. Okay, by condition 2, and this quantity is also in W. So the sum of two quantities, I mean the sum of two elements in W will always be in W. So that's why this thing is in W. Okay, and since it is an abelian group, so if I take that addition, since it is in addition, this is an element in W, as this also is an element in W. So if I add two elements of W, I'll get again in W, because since addition is closed in W. Okay, since addition is closed in W, we get this is also in W. Okay, so the second condition is I take two scalars, alpha plus beta, and I take one vector from W. Then this can be written as alpha x plus beta y. I have to just show this is in W. Now this quantity, okay, this quantity belongs to W. Okay, because of the condition 2. In the same way, this quantity also belongs to W, and this is addition is closed. So this belongs to W, this belongs to W. So if you add two elements of W, the whole thing will belongs to W. So we have proved this. So this next one, we have alpha beta applied on X. Okay, alpha beta applied on X. Just fine with this. Alpha beta applied on X. Why we have got this? Also, one more thing I want to explain you here. So here this belongs to W. It's very clear. But see, let us check from the beginning. If I take alpha X plus Y. Now this X, okay, X belongs here. Let me write here. X and Y belongs to W. Okay, and W is a subset of V on it. So this implies X comma Y belongs to V. So since V is a vector space, this condition should be true. Since V is a vector space, this condition should be true. So we get here alpha X plus alpha Y. Okay. Now this is an element of W. This is also an element of W by condition 2. So this whole thing will be an element of W. Same way, point number 2 was what? Alpha plus beta applied on X. Now X belongs to W, so it still belongs to V. So this condition, V is a vector space, this condition should be true. So we have alpha X plus beta X. Now this belongs to W. Okay, this belongs to W. This also belongs to W. So this will get what? This whole thing will be in W. Point number 3 was alpha beta X. Okay, alpha beta X. Now this, okay, if I look this one, alpha beta X. Now X is in W, so X is also in V. Since V is a vector space over the field F, we can write this as alpha beta X. I'm using the condition that V is a vector space over F. Okay, since V is a vector space over F, I can write this. Now this belongs to W, easily we can see by condition 2. Now if this is in W, and the whole alpha into an element in W will also be an element in W, say by condition 2. So this belongs to W. Okay, and the fourth one is 1 into X. Okay, 1 into X. Now X is in V, so 1 into X is also X by using the condition V is a vector space over the field F. Okay, so this also belongs to W. Now all the four conditions of the vector space is satisfied, hence W is a subspace of V over the field F. Thank you.